Hi, I'm Alistair, and this is part of a series of videos where I'm looking at ways that you can create touch-free interfaces for your Arduino projects, such as for an escape room puzzle controller. Now, in previous videos, I looked at an infrared sensor, an ultrasonic sensor, and a laser time of flight sensor. And even though these are based on different technologies, they share the same underlying approach, which is that they emit a signal of some sort, and then they wait to see whether that signal is reflected back to the sensor. If it is, it suggests that there's some sort of object in the way, and that can be used as an input. Now, in this video, we're going to be looking at a capacitive touch sensor instead, and this works following quite a different approach. So let me show you it in action. So this is the module I'm using, and you can see from the label at the top of the board that it's based on the CAP1188 chip, which you can see here. Now this runs at 5 volts, so I've got the ground and the V-in pin connected to ground and 5 volt on my Arduino Nano here. And I'm using the I2C interface to transfer data. So I've got the SCK line, that's the system clock line, connected to my Arduino pin A5, and the SDA, that's the data line, connected to Arduino pin A4. Now that's actually all the connections that's required to the processor, but you'll see that there's still lots of other pins on the board. And one of the reasons for that is that this board, unlike all the other sensors we've seen in this series of videos, this is actually capable of detecting 8 separate inputs. So on the right hand side of the board, we've got these pins labelled C1 to C8, and they correspond to 8 different input lines. And on the left hand side opposite them, we've got pins labelled L1 to L8. And those are the corresponding output pins, which will be driven high or low depending on whether an input detected on the corresponding input pin. There's also actually LEDs on the board that are going to light up to show the status of those inputs as well. So to understand how these inputs work, we need to understand a little bit about capacitance. So different objects have different capacitance, so their ability to hold electrical charge. Now, human skin, for example, is made predominantly from water, and water has a different electrical capacitance from air. So these pins at the moment, if I touch my fingers onto them, you'll see that the LEDs on the other side light up. That's because when a continuous contact is made with my finger here, we are able to change the capacitance of this pin. That's detected by the processor board in the middle, and it corresponds to an output being written to one of these pins, and the LED lights up. Now that's all very well, but the whole point of this series of videos is we're trying to avoid touch input. We want something to be detected at a distance. And in order to do that, what we need to do is to increase the surface area of these pins. When we do that, it kind of increases the sensitivity, it increases the electrical field area, and if we put our hand into that area, it will actually affect the capacitance sort of by induction. It doesn't need to make a continuous contact. So to do that, let me put this down on the surface here. And to increase the surface area of these contacts, what you'll see I've made is this little copper outline of a hand. So this is just a copper wire which I've bent round, and you'll see I've got a little wire here which I'm going to connect to the C1 pin. So what I've effectively done, I've only plugged it into this one input here. I've left the other ones alone. And if I just reconnect the Arduino now, so the surface area of that C1 pin is now much more sensitive, and if I simply hold my hand above the copper wire, you'll see that I can actually make that LED light up corresponding to the C1 input from a distance. Now that's a distance of about 5 centimeters, and if I move my hand straight back, that is the trigger point. So that's a distance of about 10-12 centimeters above the board. You can see the LED lighting up as it detects the change in capacitance caused by my hand being in proximity to that copper wire. Now, what's really interesting about this type of sensor, rather than the other ones we've looked at, which is the infrared and the ultrasonic and the laser sensor, is that this doesn't need any kind of line of sight. We're not emitting a signal that bounces back at all. So what that means is that I can actually cover over the sensor with a board like this, and then place my hand on top of the sensor, and you'll see that I can be detected. So this is through a distance of still about 10 centimeters and through a wooden board, which for something like an escape room puzzle is great because it means you can completely contain your sensor electronics behind a wooden or a plastic or a perspex sheet. You can't do it behind a metal sheet because that itself would change the capacitance of the sensors. But you can see it's actually a really good way to get effectively a hidden sensor that will detect touch input at a distance. So this is a fritzing diagram that illustrates how you could wire a component like this to an Arduino. And the particular module I'm using actually has a choice of two different interfaces you can use. It has I2C, which is what I'm using in this example, and it also has SPI, which is an interface I've used in other projects, such as connecting to an RFID sensor. Now, the reason I've used I2C in this case is because it's slightly simpler from a hardware point of view. It requires only 2 wires for the interface. It has a clock line, which is this yellow one that goes to A5, and it also has a data line that connects this SDA pin to A4. Now, in an I2C network, this data line is what's called bidirectional. So it carries commands from the Arduino to the sensor, and it also carries data back again from the sensor to the Arduino. If you were to use the SPI interface instead, that takes a few more different pins on the Arduino, and one of the reasons is because the data line in an SPI connection is not bidirectional. So the data from the Arduino to the sensor happens on the MOSI pin, and the data back again from the sensor to the Arduino happens on the MISO pin. So that data is kind of split out depending on which way it's travelling. Another difference is that on an SPI interface, when you've got multiple devices, you need to know which one is using the network at a time. And on an SPI interface, that's done by connecting another line to this CS pin, or a slave select pin. And when the Arduino writes a low signal to that line, it means that this device is allowed to use the network. So that would use another pin on the Arduino. If you're using an I2C interface, however, you have a separate hardware address assigned to each device on the network. And you can actually do that on the board here by connecting this AD pin here to one of a number of different solder pads on the reverse of the board. And once you've done that, that's kind of like a fixed hardware address from then on, which you can refer to in code. So it doesn't need a pin on the Arduino to refer to the device. Instead, you refer to the address that's been set, like I say, either by a solder or sometimes by a jumper as well. So that's it in terms of the connections between the Arduino and the sensor board. You can see we've also got 5 volt going to V in and ground going to ground. On this side of the board, this is where we connect the kind of terminals which we're actually going to listen to touch input from. So you can see here at the moment I've just got one wire connected to C1. When certain capacitance is detected on that pin, it's going to light up the L1 on this line as well. And you could plug a device into L1 here if you want to make a hardware connection when that one lights up. And we're also going to be able to access those values over software through the data that's being sent through this SDA pin here. If we wanted to add more touch devices, you can add up to 8 different sensor inputs on this side. Each has a corresponding LED on the board and a corresponding L pin here, and they would all be available over software through Interrogate as well. So it's really quite a powerful and flexible device actually. You've got the choice of how you interface to it. You've got the up to 8 different inputs you can detect. It has visual display on the board for each one that's detected, and it also has a hardware and a software output of all of those values. So it's a neat little board to use. So here's the code that's running on the Arduino, and if you've been following along with this series of videos about different touch-free sensors, this will probably look pretty familiar to you, because a lot of the structure is the same as I've used in the code on the other sensors. But there are a few specific details that are different about this sensor, so we'll try to step through those in a little bit more detail to explain how this works. So we start at the top of the code with this section that's labelled defines, and we have a line here that says define sensitivity 0x0f. So what a define means is you can think of this a bit like a search and replace. Every time we see the word sensitivity appear in the code anywhere later on, it's going to get replaced by this 0x0f value. So for example, if we scroll down a little bit here, we can see the word sensitivity appear in this line. So why are we using 0x0f? Well, this is a binary representation of a single byte value, and we're going to set this value to one of these possible options above in order to set the sensitivity of the board. So you can see I've got a total of 8 possible values that we can set it to there. We can have 0x0f, 0x1f, 0x2f, all the way up to 7f. And they correspond in a descending order of how sensitive we're going to be. So this is 128 times sensitivity all the way down to 1 times sensitivity. Now, why are we writing them like this rather than just writing them as numbers from 1 to 7? Well, this is due to the fact that on the board itself we have a registry of different values. A little bit like on your computer, your Windows registry has a series of different values that are written that control various settings. But the sensitivity doesn't actually have its own unique registry value. It only uses half of a byte value, and it shares that byte with some other data that we don't want to vary. So that's why all of these possible values that we set these to have an F at the end of them. We're going to use that as what's called a bit mask. And this is all a bit complicated if you've not worked with bits in coding before. I'll try to explain it as simply as I can. But we're going to use this in a function later on that basically says retrieve only the first half of this byte value, and then change this first part of it to either be 0, 1, 2, 3, 4, 5, 6 or 7. And then where this F is going to be, we're going to write back whatever the value was there already. So the F kind of signifies leave that part of the byte alone, and this first part here we're going to write a value to, which is going to change the sensitivity of the code. Okay. So in terms of actually what value you want to set here, well, you're going to have to do a little bit of experimentation really. You will probably want a value somewhere in the middle, so I'd say 0x3f might be a good place to start, but it's going to depend on the size of the conductor that you use. So if you use a metal plate, or if you just have a small pin or a screw or something like that, that's going to vary. The larger the surface, probably the less sensitive you're going to want to be. Otherwise what you'll do is actually you'll be detecting from too far away and you'll get a noisy signal. So probably something like 0x3f is a good place to start, in which case you'll simply put a 3 value there, and from then on every point of the code that refers to this sensitivity is going to use this value here, and I'll show you a bit later on exactly how that gets worked. So then we get into the includes. So this is where we include any external code libraries which we're going to add into our code. We use the wire library. This comes with the Arduino IDE, and it's what we use for connecting to any I2C device. And then we also have this library, which is going to contain specific functions related to the Cap1188 module. I'll include this in the download as well anyway. So that's just going to wrap up some of the functionality that makes it a little bit easier to retrieve the packet of values that say which sensors have been touched. Then we'll define some constants. So I'm using an LED pin on the Arduino Nano itself. So this board actually has LED pins on the module that will light up to detect when a touch input has been detected, but we'll also define an LED pin on the Arduino. That just makes sure that we can see that the the touch has been detected, and by the Arduino code, not just by the sensor hardware on the board itself. And that doesn't have to be an LED. You could have a relay pin attached to that, or to drive any load you want. But when a touch is detected, we're going to drive that signal high. Then we go on to the globals. So this cap object here, we're going to create an instance of the cap118 class, and this is one of the classes that is defined in this library here. So that's going to wrap up the functionality that comes with this module. And we'll also define this flag here that says detected. This is going to let us know whether we've got a new detected object, or whether we've got an object that we already knew about in the last frame that's just been held in the range of the sensor. So then we go into setup, and this is a little bit more involved again than in some of the previous examples. So we begin a serial connection and we write out the name of this script and the date in which it was compiled. And then we've got this line here, which has got quite a big comment attached to it. So I mentioned when I showed you the fritzing wiring diagram, the fact that when you use an I2C interface to connect to a device, every piece of hardware on that I2C network needs to have a unique address. And you actually set that via a physical change you make on the board. So the default for the module I've got, and for most of the Cap1188 modules I've seen, the default address is 0x29. And you'll see that I've passed that in this function here when I begin a connection to the capacitive sensor. Now, if this is the only I2C device in your network, or if all the other devices you've got have got their own unique addresses, you do not need to change that at all. You can just leave that line exactly as it is. But if for whatever reason you have some sort of conflict with another device and you need to change it, I've written here what you need to do to assign an address of either 0x28 or 2A, 2B or 2C. And what they all do is they require you to connect that AD pin, which I showed you in the wiring diagram, to ground, to either to 3 volts, in which case it's a simple wire connecting it to 3 volts. We'll set it to this address. Or you can connect it to ground, but via a different value resistor. So if you solder a resistor between AD and ground of this value, you can choose one of these different addresses as well. Now, the reason why this comment is so long is because it's a little bit complicated. On my board itself, there is already a 150 kilo ohm resistor on the board between AD and ground. That's how come we've got this value in the first place. If you were to read the data sheet, which I've linked at the top of the code here, so here's the data sheet for the board. If you were to read that, it will give you some resistance values you need to set, which are 120, 100 and 82. But I've written different values here, and the reason for that is because if you're going to leave this 150 kilo ohm resistor already attached, you're then attaching another resistor in parallel with that. So to kind of make the numbers add up to what it says in the data sheet, you actually have to add slightly different values than what it says, because you have to account for the parallel resistance with the resistor already on the board. That's a little bit complicated, but in the vast majority of cases you shouldn't have to worry about it anyway. You can simply use the default address, which is 0x29, and that is what I've got included on this line here. So assuming that's successful, we'll write a serial message here. We'll configure our output pin, which we're going to drive high when a touch is detected. And now we get to the next slightly complicated bit again. So this was about that sensitivity value we set at the top. So If you recall, this was a byte in the registry of the capacity sensor, and it's a byte that has sort of two halves. It has a low half and a high half, and the sensitivity is in the high half. So first of all, we're going to call the read register command. So this is going to retrieve the byte value that is on the sensor at the moment, and we're going to pass, so this is the address 0x1f. That is the address that contains this registry value we want to receive. Now we're going to use this ampersand 0x0f here, and what this is telling us to do is to this f here represents a bit mask where all of the bits have been set to 1. So it's saying, okay, copy all of the bits from the lower half of this value, because that is what f means, but zero out all of the bits in the upper half of the register. That's what the 0 corresponds to. So it says basically retrieve this value here, so whatever the value is in the memory address 0x1f, give me the values that are currently in the lower half, but just blank out the top half. And then what we're going to do is we're going to fill in the top half with the sensitivity we chose at the top, but leaving the lower half that was already there. And then finally we're going to write that back to 0x1f, which was the address we read it from in the first place. So if you've not used bit packing and bit values and this kind of bit operators in the past before, this can seem a little bit scary, but it's really not too bad. It's a very efficient way. If you're working with Arduinos or other microprocessors and you want to pack a lot of data into the smallest amount of room possible, let's say you want to store a load of values that are just on-off values, so they only need to have the values 0 or 1. If you were using an int data type, let's say, to store those values, that's really inefficient, because an int can hold a massive range of values, but you're only giving it 0s and 1s. You really only need to have a single bit that could be a 0 or 1, and you can get 8 bits into a single byte of data. So you've got this 10, 10, 111, and you're still only using 1 byte to store that. That's effectively what we're doing here. We're reading a single byte of data, but then because we only really want to edit one, or specifically half of that byte of data, that's why we get this slightly complicated looking set of instructions here. But that's all it's doing. It's setting the sensitivity which we assigned at the top of the code here to one of these values here. So make sure it's always 0x and then a number between 0 and 7 and then an f at the end. So long as you follow that format, you kind of don't need to worry too much about exactly what's going on here. This will just work as it is. In the next section, we define 3 different functions that define the behavior that we want to occur based on the 3 different possible input actions that we can detect from the user. So the first one is when a new input has been detected. So this is the equivalent of a button being pressed for the first time. And when that happens, we're going to write a high signal to the LED pin. So that's going to make the LED on the Arduino light up. Remember that the LEDs on the sensor board itself will kind of light up automatically. We don't need to do anything about those. We'll write a message to the serial monitor, and we'll also set this detected flag to be true so that we know in the next frame that we could already detect an object at this point. This is input held. So this gets called in a situation where we already had some sort of input in the previous frame that we knew about, and when we check again this frame we can see that it's still there. So the hand has been held in position, or whatever conductive object it is still there, and when that happens we will simply print this sort of line of dots to the serial monitor just so we know that it's still active. If you wanted to design a puzzle that required players to hold their hand for a certain amount of time, let's say, or like a time delay before something was activated, this is where you'd add the logic to define that kind of behavior. So you could have a counter, let's say, that's incremented for the number of seconds which this is called for. And we've also got input removed. So this occurs in the case where there had been something that was detected in the last frame, but when we come to look this frame, the sensor does not report it anymore, so it must have been taken away. So this is the equivalent of releasing your finger from a button. And when that happens, we will turn the LED off, we'll write another message to the serial monitor, and we will update our detected flag so that on the next go through we know that there wasn't an object present in this case. And then we go into the loop. So on every turn through the main program loop, this just goes round and round forever. The first thing we'll do is we will retrieve the value from the sensor that lets us know which inputs have been touched. So this touched method will give that to us, and it will give it back to us as a single byte value. So 8 bits corresponding to the 8 different sensors. So an example value that this might have is something like this. So we've got 010, 0001. So this would let us know that the first sensor had been touched. We've then got the second, third and fourth not touched. The fifth one is touched, not the sixth. And the seventh one is touched and not the eighth, for example. So if we want to take some action based on whether a particular one is being touched at the time, what we need to do is we need to look at the bit that's in a particular position in the byte order. So we start at the right hand side and we shift left the number of bits of the sensor that we want to check. And that's what we're going to do in this section here. So to check the very first value here, this one at the end here, to see whether that is equal to a 0 or a 1, what we do is we take a 1 and we shift it left by the index of the sensor that we want to look at. So if we want to look at the input that's labelled C3, for example, we would take a 1 and we would shift it to the left 3 times. So in that case, we would set sensor index to be 3, for example. Or you could do 4, 5, 6, or 7, for example, to check all the different sensors in turn. Or if you wanted to, you could put this in a loop. So you could loop over all 8 values, and let's say, if they were pressed in a particular sequence, or if they were all held down at the same time, or however you wanted to define the puzzle logic. But to test a particular value, which is what we're going to do here, we'll first of all input the index, so a 0-based index of the sensor we want to check, and then we write code that looks a bit like this. So again, this is one of these bit functions that you might not have seen if you're not used to, but what it means is to shift along a bit a certain number of places as specified by this. So we'll look at that value. Now, if in the last frame we didn't have an input detected, that means that there's a new input detected this frame, and we'll call the function which we defined up here. So this is where we light the LED and we say that there's a new input detected. If there is an object detected this frame and there also was one last frame, well, that's when we call the input held function. So this is where we previously were able to detect someone's hand or whatever it was, and it's still there this frame. So this is a continuous input, is the equivalent of a button being held down. Otherwise, if we fall into this section of code here, well, this means that the touch that we're looking for at this particular index position wasn't detected, so it is equal to the value 0 in this string here, which suggests that there wasn't a touch there. Well, if that's the case, but there was one last frame, well, that means that the input must have been removed, and we'll call this input removed function instead, and that's the one that clears the LED, updates the serial monitor, and then we will set detected false, which means that on the next go through, the next time round that we do detect an input at this value, we know that it is a new input, and we will call input detected again. And finally, we'll just add a short delay just before looping the code for the next time round over and over. So this sensor works in quite a different way from all the other ones we've seen so far this series, because it doesn't emit any kind of signal that needs to be reflected again, And that means it doesn't need to have line of sight to be able to detect a user input. Now that makes it a great choice for use in an escape room game, because that's where we want players to have this kind of magical interaction with the props around them, and we want the technology to really be hidden away. And with a sensor like this, you can actually have it completely contained inside the body of a puzzle prop or other component, and players will never know it's there. They just see the results of their actions being detected. Now, in the example, I only used a single one of the inputs here, but as I said, this can support up to 8 inputs simultaneously. One thing you need to be aware of is that those inputs need to be sufficiently spaced out that you don't accidentally trigger more than one at a time as you move your hand between them. And the other thing to be aware of is, like many of the other sensors, this will be affected by environmental conditions. Particularly if you have this placed near any metal objects, they will affect the capacitance on the pins and you will need to adjust the sensitivity accordingly. But I showed you how to do that in the code example earlier. So in summary, I think these are very powerful, very flexible little boards, and I think there's actually lots of ways in which you can use them to create completely touch-free interfaces in your projects.